You swing at a fly. Your brain has already given the order. Your hand is already coming down, and it misses. Not because you got unlucky, but because the fly's nervous system processes the threat and launches its escape more than 10 times faster than your own brain manages to complete even the simplest reaction to danger. While your eye is still assembling the picture of that motion, the fly has already calculated a trajectory, picked a direction, and pushed off with its legs. Now picture this. This creature showed up on Earth tens of millions of years before the first dinosaur, survived the extinction that wiped those dinosaurs off the face of the planet, and hasn't lost its footing since. Or rather, hasn't lost its six-legged footing. And each of those legs, by the way, can taste. It has no ears, but it does have a built-in gyroscope, and its brain is about the size of a poppy seed. Yet its reaction time is among the fastest in the entire animal kingdom. And on top of all that, it lives less than a month in the wild. We call it annoying. We ignore it, wave it off, forget about it a second after it flies away. But maybe that's a mistake, because by every measure evolution has to offer, we're looking at one of the most successful organisms in the history of the planet. Here's what we're going to cover over the next half hour. How is a creature built that reacts to a threat faster than you can blink? And why do its eyes and legs work in ways you probably wouldn't expect? How did an animal the size of a grain of rice manage to survive a mass extinction that wiped out nearly all life on the planet? And why will it probably outlive us too? And finally, the uncomfortable question. If the fly is really as harmless as we like to think, why has it stood beside some of history's worst epidemics for as long as humans have kept records? The answers will unfold gradually, and some of them may completely change how you see this insect by the end of the video. Let's start with that missed swat, because it holds the first and probably the most telling fact in this whole story. The fly isn't outrunning you through raw speed in the usual sense. It's not faster than a ping-pong paddle, and it's certainly not faster than your hand in terms of pure movement speed. The real answer is that it experiences time at a fundamentally different rate. Every living creature's speed of perception comes down to something called flicker fusion frequency, the threshold above which a flickering light stops registering as separate flashes and blurs into what looks like a steady glow. That's why old fluorescent lights don't look like they're flickering to us, and why a strip of individual film frames looks like smooth motion. Because the human eye processes the world at roughly 60 cycles per second, and anything faster than that blends together into one continuous stream. In a fly, that number runs from 200 to 250 cycles per second, roughly 4 times higher than ours. And if you could borrow a fly's eyes for a moment, the world around you would suddenly seem to slow down, the same way it does in a movie's slow motion shot. Except for the fly, that's just an ordinary Tuesday. What makes that speed of perception possible is the compound eye, an intricate structure built from several thousand individual light-sensing units, each with its own tiny lens and its own narrow angle of view. A housefly has roughly 4,000 of these units in each eye, and together they add up to something close to a full circle of vision, with very few blind spots. The image that produces isn't especially sharp. A fly won't make out fine print or a detailed pattern, but the system is built for exactly one job: catching the smallest shift in movement around it fast enough that the escape response kicks in before the threat even gets close. Here's where a second number comes in, an even more striking one. From the moment a fly's compound eye registers sudden movement to the moment its wings are already turning toward escape, roughly 20 milliseconds pass. For comparison, the simplest human reflex, yanking a finger off a hot stove, takes at least 100 milliseconds. and a conscious response to a visual cue, like that swat with the fly swatter, stretches out to somewhere between 200 and 250 milliseconds. While your brain is still putting together the picture of hand coming down, the fly has already decided where to go and is already airborne. But fast eyesight alone isn't enough to dodge a strike in a fraction of a second. The body still has to know exactly how to move without losing its balance while reacting that quickly. That's where the fly is hiding another piece of engineering that makes you wonder whether insect is even the right word for what you're looking at. Most flying insects have two pairs of wings. A fly has, you could say, 1.5. Over the course of evolution, its second pair shrank down into two tiny club-shaped stalks behind the main wings, called halteres. And at first glance, they don't look like they do anything at all. In reality, they're one of the most elegant pieces of engineering in the insect world. Because the halteres beat in the opposite phase from the main wings, at the exact same frequency, and since that main pair of wings beats around 200 times a second, any deviation in the fly's flight path instantly throws that beat out of sync. The fly's brain reads that disruption almost instantly and corrects its flight, essentially running on a constant stream of gyroscope data, which is exactly why a fly can pull off sharp turns, launch straight upward, and spin a full 180 degrees in midair in a fraction of a second. Take away the halteres, and it literally can't hold a course and drops out of the sky. The most deceptive part of a fly's anatomy, though, isn't in its eyes or its wings. It's in its legs. When a fly lands on your sandwich, it doesn't start eating right away. It wanders around the surface for a moment first, almost as if it's thinking it over. What's actually happening is that it's already tasting the food. And it's doing that not with its mouth, but with its feet. Because the tips of its legs carry chemoreceptors, tiny sensors that detect sugar and other chemicals through simple contact with a surface. And every step a fly takes doubles as a taste test. That's how a fly can decide whether a given surface is worth sticking around for before it even lowers its proboscis. It can also walk somewhere no vertebrate could hold on for even a second, upside down across a ceiling, straight up a pane of glass. The secret lies in a pair of tiny pads at the tip of each leg, covered in microscopic hairs and a thin film of fluid, and that film creates a molecular-level grip on the surface, letting the fly stick to glass with every step, while small claws at the very tip of each leg help it peel back off in time to take the next one without getting stuck. Put it all together, eyesight running on a different clock than ours, a gyroscope standing in for a second pair of wings, a tongue built into the tips of its legs, and the ability to walk across a ceiling, and you get the portrait of a creature that looks a lot more like a miniature aircraft with a built-in sensor suite than just an annoying bug. Which raises an obvious question. If nature packed this much engineering into this one creature, why do we still treat the fly as something insignificant? The answer has less to do with anatomy and more to do with history, and a much longer history than you might expect. The order of true flies, the one our subject belongs to, is called Diptera, two-winged, named exactly for the fact that its second pair of wings turned into those gyroscope halters. And going by the fossil record, that order is roughly 260 million years old. To put that in perspective, flies, in one form or another, existed before the first dinosaurs ever appeared, watched the entire rise and fall of the dinosaurs from start to finish, survived the asteroid that ended the Cretaceous period and wiped out 3/4 of all species on the planet, and simply kept going afterward, as if nothing much had happened. The secret to that kind of staying power has nothing to do with the toughness of any single fly. Swatting one isn't hard, as you may have just proven to yourself. The real secret is in the math of reproduction, which works with an efficiency that looks less like biology and more like a computer algorithm. Over her lifetime, a single female housefly can lay anywhere from 350 to 900 eggs across several batches. And under the right temperature, the entire path from egg to a reproduction-ready adult takes only 7 to 10 days. That means a single warm season in a temperate climate can produce 6 to 8 overlapping generations. And the overlap matters just as much as the number. Because these generations don't take turns, they stack on top of each other. While one batch of eggs is still developing into larvae, the next batch has already been laid. And a third generation is already flying around looking for a place to lay a fourth. That turnover speed is the actual secret behind the fly's evolutionary longevity. When a population effectively resets itself every week or two, natural selection gets an enormous number of chances to fine-tune the species against changing conditions. Far more chances than animals that only reproduce once a year ever get. That's exactly why flies develop resistance to insecticides at such an alarming pace. Where a person is counting on getting one good season out of a chemical treatment, a fly population cycles through so many generations in that same stretch of time that a random genetic resistance can take hold and spread through the population before that chemical is even pulled from the shelves. Add to that the fact that members of the order Diptera have colonized every continent except, arguably, the harshest stretches of Antarctica. And you get a species that can be called one of the most successful multicellular organisms in the history of the planet, without any exaggeration. But every evolutionary success story has a flip side. And the fly's flip side is a lot less pleasant than a fast reflex or a gyroscope where a second pair of wings used to be. It's easy to assume a fly is simply irritating. It buzzes, it lands on food, it gets on your nerves. But the real problem runs deeper than irritation, and it comes from the very same trait that makes the fly such a successful species. It lays its eggs and feeds wherever organic matter is decomposing. In garbage, in manure, anywhere sanitary conditions are less than ideal. Which means every time a fly lands on one of those sources and then lands on your plate, it's carrying with it, on its legs and mouth parts, everything it picked up along the way. Systematic reviews studying the microbes carried by houseflies have linked this insect to more than 100 different pathogens: bacteria, viruses, protozoa, and parasite eggs. And among the most serious are the organisms behind typhoid fever, cholera, and dysentery. Precisely the infections that have historically followed wars, refugee camps, and any large group of people living without proper sanitation. This isn't just an abstract laboratory theory. In 1898, during the Spanish-American War, the United States War Department assembled a special commission led by Major Walter Reed to investigate a typhoid epidemic sweeping through Army camps, and the commission toured camps across several states, its final report identifying flies and direct contact with fecal matter as the primary route of transmission, giving contaminated water a far smaller role than expected. Flies were laying eggs in latrines, then landing on soldiers' food and dishes, carrying bacteria along in a matter of minutes. The mechanism behind that transfer is simple, and no less effective for being simple. A fly doesn't bite or inject anything the way a mosquito or a tick does. It's a mechanical carrier, in the most literal sense. And bacteria and parasite cysts simply stick to the hairs on its legs and body, some of it passing through the fly's own digestive system and coming back out later in its saliva or waste, deposited right on whatever surface it happens to land on. That, incidentally, is also the source of a behavior a lot of people have noticed without quite understanding it. Before a fly eats anything solid, it spits a drop of digestive fluid onto the food to partially dissolve it from the outside. And that's exactly the moment when whatever the fly was carrying from its last stop ends up on the surface. What you're left with is an uncomfortable picture. The very trait that makes the fly one of the most successful organisms on the planet, the ability to reproduce explosively almost anywhere, including places most people would rather not think about, turns into a real health risk for anyone living near poor sanitation. It's worth avoiding the opposite overcorrection too. Today, with modern sewage systems, refrigeration, and basic kitchen hygiene, the odds of catching something serious from a random fly landing on your sandwich are statistically low for most people in developed countries. And the real danger concentrates specifically where there's no access to clean water or proper waste disposal. The fly functioning there more as a visible indicator of conditions where disease was already primed to break out, than as a standalone root cause. The fly really is tied to some of the darkest chapters in the history of epidemics, and that's a well-documented fact, not an exaggeration. And yet, its own lifespan, set against all that grim statistical weight, looks almost tragically short. And that contrast is where things take a philosophical turn. An adult housefly lives, on average, somewhere between 2 and 4 weeks in the wild. A bit longer under ideal conditions, though most individuals don't even make it a full month before falling prey to birds, spiders, or simple bad weather. At first glance, that's a strange combination. A creature running one of the fastest nervous systems in the animal kingdom, capable of reacting to danger faster than a human eyelid can finish a single blink, given by nature a lifespan shorter than most people's summer vacation. But look closer, and there's no contradiction in that combination. It's really two sides of the same evolutionary strategy. At this reproductive speed, what determines the fate of the species is the number of generations that cycle through in a season, not how long any single fly happens to live. And a lightning-fast reflex, in this context, works as a tool for surviving long enough to reproduce, lay eggs, and pass that same reaction speed on to the next generation. Every individual fly plays its part in the continuity of the species, and once you look at it that way, its own short life stops looking like a tragedy and starts looking like a remarkably rational division of labor across generations. There's one last loop worth closing here, the one that ties together the fly's speed of perception, its short life, and the grim reputation covered a moment ago. A fly doesn't stop mattering after its own death, or rather, it doesn't stop mattering even when it's not landing on a living person, but on the body of someone who has died. This is where its closest relatives, blowflies, take over, and their behavior turns out to be so predictable that it became the foundation of an entire forensic discipline, arriving at a body within minutes of death and laying their eggs in natural openings and open wounds. The larvae that hatch move through 3 distinct, strictly sequential stages of development, and the speed of that development depends directly on the surrounding temperature, which means that by identifying exactly which stage the larvae on a body have reached, forensic entomologists can pin down the time since death to within a few hours, even when a body isn't discovered for weeks, long after the usual markers have stopped being useful at all. So it turns out that the very creature living faster than we do, perceiving the world in slow motion, reacting in milliseconds, cycling through a dozen generations in the time it takes us to get through one season, is capable of telling us about time more precisely than most human instruments, simply by being present and following its own predictable life cycle. The fly you wave off your kitchen counter without a second glance is more intricately built, moves faster, and leaves a bigger mark on history than that clumsy missed swat at the start of this video would ever suggest. A creature we brush off without a second thought, perceives our hand in slow motion, reacts faster than our own brain can, walks upside down across ceilings, and tastes the world through its own feet. It's older than the dinosaurs, and it will likely outlive most species alive today, including possibly our own, because its secret to success rests on the speed of its generational turnover, a pace that lets the order Diptera adapt to change faster than that change can turn deadly. And at the same time, this same fly stands next to some of the darkest chapters in the history of epidemics, simply because it does, with total efficiency and zero malicious intent, exactly what evolution built it to do: move between food sources as fast and as often as possible. Each individual fly, meanwhile, lives an almost pitifully short life, shorter than most people's summer break. But that short life is precisely the price the species pays for the right to have existed for 260 million years and counting. Which part of this surprised you more? The speed of a fly's reflexes and the anatomy behind them? Or the fact that you're looking at one of the oldest and most successful survivors on the planet? Let us know in the comments whether you've ever noticed a fly tasting a table with its feet before landing on your food. And if you're up for it, next time we'll take a closer look at blowflies on their own, because their role in nature and in forensic science deserves its own investigation.